No, I'm going to do a first question, and then I will open it up, because in that spirit of synthesis, it's quite interesting, because one thing that one sort of slightly paradoxical, puzzling issue we've all addressed is that we keep pushing complexity back. So the evolutionary theory says all the complexity comes from the world, right? That's what those equations do. They extract order from the world and put them in the organisms. There's nothing in organisms that wasn't there. So that's a bit of a limitation of the mathematics. And then both of you, Karina saying, actually, the ensemble of behavioral variation just gets amplified, so it's there. And now you're telling us, actually, empirically, they're all there, right, in the Cambrian. So there's this interesting point that, I mean, how do we address this question of the evolution of complexity if we just ultimately say the complexity was always there, and we're just, presenting it in different ways?
Beats me.
Yeah, I mean, I think as far as my own work is trying to see, to me, it's a lot more about the mechanisms, like trying to see what are these, not the building blocks, but the operations that can happen, right? And the operations of self-organization, the operations of putting together individual units, and then trying to slowly build and see what comes out of that. Like all of this part about the reason I'm so interested in the origin is because I'm really curious how much can already happen at the origin, right? How much can we harness what was already there, and how far can we push, how complicated the system can get. And the fact that with an incredibly simple model, we can get, 6 different life cycles that are, at least bear some resemblance to the life cycles of multicellular organisms today, to me is indicative that there's actually a lot that can happen very quickly, and so in that sense I agree with Doug. And then I think one of my favorite books is Francois Jacob's The Actual and the Possible. And I think we are a lot tend to be biased, or at least theoretically have been biased by by the actual in asking the questions about how things have happened. But this kind of way of building it up from the bottom up can actually tell us a lot about not just the actual and the possible, but what are the right questions to ask of the actual and the possible. So
yeah, I mean, I think. So if you take gene regulatory networks as a specific case, I think one can begin to ask the question about to what extent some of the some regulatory patterns are almost fated to evolve. Does the nature of gene regulation, the fact that you're limited to a certain suite of sub-circuit network interactions, mean that some of the trajectories of those patterns are likely to evolve in any context? Because the question that Francois Jacob began with, the possible and the actual, which was initially applied in the context of Earth, in the context of astrobiology and the work that NASA and also NSF have funded for the last 2.5 decades, is we have n equals 1, but we'd actually like to know what is possible elsewhere in the universe. And that's a wonderful question that I think has focused a lot of work on trying to identify these universal themes of biology.
All right, thank you. So I have a question for this last talk about how would you know? And let me try to couch it clearly. So you put on the table the idea that there might have been some vestigial machinery in very ancient life that highly circumscribed what could have happened later. And so
I'll go with circumscribed rather than highly circumscribed.
Understood. Okay, they circumscribed so that's an idea that some of the possible pathways were not preordained, but let's say prejudiced early on. And then there's another idea that, well, no, none of that's true. It just sort of happened by whatever. Now, we decide in science the difference between things, ideas, experimentally. So the question is, other than what experimental tests have you possibly got other than making speculations about the genomes?
Well, the wonderful thing about the fossil record is that we have, for animal evolution, we have 600 million years of experiments. I mean, it's true, we cannot go back in the lab and recreate the conditions of the Cambrian. But we do know what trajectories different lineages took, and we do have comparative data from extant taxa now. Yeah, that's a different kind of science, I think, than population genetics, for example. But I think it's a no less valuable approach to understanding historical patterns.
So let me just follow up, because this is a question of focus, with science focus. See, there's a really provocative idea, and something happened. I mean, we're here, so something happened back then. And yes, the fossil record is there. It gets a little scanty in the Precambrian, but you're the expert in that. And there are extant taxa that you can study genetically. That's true. Now, so you've got that, and now we're arguing. And the question I'm basically putting to you is there enough experimental evidence to decide this one way or the other? Because if there isn't, then it's a bad question.
To decide which question?
Whether what happened evolutionarily was partly preordained, or whether it was just a sequence of Gouldian accidents.
I think there's enough evidence now to suggest the answer to that question. And I think within the next 2 decades or less, there will be experimental approaches that will allow a more rigorous answer to that. And so the specific thing I would talk about is actually a grant that I was working on with Eric Davidson when he died, which is something that Eric called experimental regulatory evolution, which was by comparative studies we were able to infer the structure of regulatory networks in the past based on comparing regulatory networks that exist now, which means that we should be able to go in, for example, to sea urchins and recreate the networks. And the specific example we were going to use was to look at the networks for gut formation 250 million years ago. That's something that's now experimentally tractable. And in fact, a different group published a paper doing that about 3 weeks ago. So I think the experimental reconstruction of some of these ancestral networks, even in metazoans, it's easy to do in yeast, even in metazoans, is something that's already possible. And I think that will answer some of these questions.
Doug, I was struck by the apparent universality of one of your conclusions, that what looked like evolutionary events, we have the origin of enormous novelty. When we look closer, it's often actually just an event of assembling existing machinery. And I'm struck by the apparent universality of that. For example, Doan Farmer ran a workshop, I think you were there, where he looked at the evolution of technology and reached the same conclusion. When we see something brand new, the people discuss the internal combustion engine. Well, okay, sort of brand new in application, but the piston was there being used in water pumps. The carburetor was there being used, I forget what for. All the pieces were in existence and being used, and somebody put them together in a new way. And the results were impressive. And that's what technological evolution typically does. That's what biological evolution typically does. It seems quite universal.
So Mark Feldman, who we all know, had a couple of really great postdocs a few years ago, including a woman Nicole Kranza, who I think is now at UCL. And she and Mark and the others in the lab did a wonderful PNAS paper where they simulated cultural evolution. And they had 4 different modes, I got 4 there. 4 different modes of technological evolution, one of them being recombination, which certainly in the simulations they did comes out to be enormously important. But the thing that actually drives the whole process is that you still need the input occasionally of what they call lucky leaps. So you still need true novelties, at least in my sense of the word novelty, as a relatively frequent input into the system to allow the combinatoric expansion that Don was talking about. And I think that's likely to be true in biology too.
Yeah. I've always been intrigued by that quote that you showed from Maynard Smith and Seth Murray about there's no law that says it has to continue, that it could have stopped at prokaryotes. Okay, and maybe you answer the question because maybe I wasn't listening. That seems extremely unlikely, given the dynamic of an evolutionary adaptive process. And I was wondering what the thinking was about it, because is there a conceptual theoretical framework or an understanding of the evolutionary process which says that, yes, it is conceivable that some time it saturates, much like growth does. I mean, if you only saw little babies and little children, you might think that growth would continue sort of ad infinitum, but it doesn't. It stops. Is that true of the evolutionary process? And I bring it up because of, could we have imagined, thinking of thought experiments, if a long time ago we had been able to project into the future about the state of human beings and society, and saw that with the continuous acceleration of innovation and the use of energy and its ultimate entropic consequences, we would drive ourselves into a threatened situation. Is it conceivable, even, that we could have stopped, or to put it now, is it conceivable that we can stop a process now? So that's a hypothetical question, but I'm wondering what the thinking is among evolutionary biologists about this statement, which I'm familiar with that statement, and I've often been intrigued that they even made it.
So I think the other 2 speakers probably have insights into that question too. I would go further back than human evolution, and I would put the question this way. So it took at least 2 billion years, and possibly, based on recent evidence, 3 billion years to get to a eukaryotic cell. If we went back in a time machine 2 billion years ago, NSF being incredibly generous and funding our DeLorean, would we have predicted multicellularity, or complex multicellularity? We already had 2 billion years of history with lots of different kinds of metabolism, but not much else.
Well, that's because time is actually logarithmic. It's not linear. That's because you're thinking as a paleobiologist, not as a physicist.
Well, and I'm very grateful for that, might I add, Jeffrey. We could do this for hours, actually. Whenever we have an audience. Well, 2 billion years is still a long time to a geologist, even if it isn't to a physicist. But I think the point remains that I'm not sure if we went back 2 billion years ago, we would have predicted, or even a billion years ago.
About prediction, but is it conceivable what they said, that it would have just stopped? That's what I'm wondering. What is the conceptual framework?
I think that
there must be a theory.
Yeah, the theory now is...
Does the theory have in it, if you put in an equation that says... We could have stopped.
The theory from a geologist standpoint is actually more geochemical. That the limitation was the external redox environment that inhibited any future evolution. You had to overcome that in order to get somewhere.
I mean, just quickly on theory, Jeff. There are basically two classes of theory in evolution, right? There's classical mechanics theory, which is there are these little orbiting things called genes, and they segregate in a certain way, and we assign two sets fitness values. So it's entirely imposed structure from humans, and we're just doing mechanics, okay? And they have fixed points. And there's absolutely nothing in that theory at all that bears on your question, not even a little. Then there's the stuff I talked about, which is there is this mechanic that sort of sucks information out of the universe and sticks it in these little memory pods called organisms. And that's bounded by the information in the universe. And in that respect, it's not so unlike saying all of the order comes from the Big Bang and we're just spending it down. So that does actually potentially make predictions, and those limits come from your ability to successfully extract information from the world. It does not tell you where that information comes from. So current theory sort of maybe can move towards the answer, but not really.
I would also add just that that statement was made a little bit in vacuum without any kind of thinking about the ecology or the interaction with the environment, right? So, in those 2 billion years, they modified the environment quite dramatically, and it seemed very slow. It was a very slow process, but at some point it was a dramatic buildup that allowed for something else to happen, right? And once you put that feedback into the models, into evolutionary models, then I find their statement puzzling. It doesn't make much sense, right? So
the only acknowledgement that the environment exists in the whole book is one sentence on page 9. And beyond that, they completely ignore those environmental.
Exactly, yeah.
Final question, then we're going to break. Jen, you have a question? No. Oh, I was just trying to get it. Yeah. So I think this comment relates to some things you guys brought up in Jeffrey's remark, maybe something I've been thinking about for a while. Maybe there's an easy answer. I think there probably isn't. And the question is optimal information processing, that is the extraction of the maximum regularity from the environment, equivalent to energy minimization? Like, when does the distinction between energy and information disappear?
Well, I view them as fundamentally distinct and actually inverse, right? So one is conserved. No, but one is a conserved concept based on symmetries, and the other one is non-conserved and based on broken symmetries. So they're related in terms of their storage costs, but I do think they're sort of antithetical concepts in some related but different, quite distinct. But
yeah. I'm thinking of the fact, Jeff. I'm thinking of the fact that the reason we think information processing happens in adaptive systems is to harness energy to do work, right? And so if information processing is optimal, what is that actually saying? Anyone want to try to address that?
Well, let's discuss it over coffee.